So this is a very exciting lesson about elementary reactions and reaction mechanisms. I know you are enthralled. So the idea behind this is it's pretty cool. It's pretty simple. You're going to be able to represent an elementary or basic reaction as a rate law expression using stoichiometry. You'll be able to identify the components of a reaction mechanism and identify the rate law for a reaction from a mechanism in which the first step is rate limiting. And that sounds like a whole bunch of mess, but it's not. So the background information here from College Board, many chemical reactions occur through a series of elementary reactions. These elementary reactions, when combined, form a chemical equation. So it's kind of like the idea behind Hess's law that you have component equations that combine, certain things cancel out, and you're left with an overall process. There is a relationship between the speed of a reaction and the collision frequency of particle collision. That was repetitive. The rate law of an elementary reaction, so that's one of the simple component reactions, can be inferred from the stoichiometry of the molecules participating in a collision. This we will definitely revisit. Elementary reactions involving the simultaneous collision of 3 or more particles are rare. It's like the perfect storm. To get 3 or more particles to collide at the right energy and orientation is very unlikely. This is some more curriculum stuff that we're going to revisit in the following notes. A reaction mechanism consists of a series of elementary reactions or steps that occur in a sequence. These components might include reactants, intermediates, products, and catalysts. When you add the elementary steps together, they should match up with the overall balanced equation of the chemical reaction. An intermediate is produced in some early step and then consumed by a later step. So it's only present while a certain process is occurring. It's not present in the overall reaction. And experimental detection of a reaction intermediate is a way to build evidence in support of one reaction mechanism over another. Okay, so here's the idea behind the reaction mechanism. It is a series of elementary steps, so basic steps, by which a chemical reaction occurs. Most reactions occur by a series of elementary steps, and basically it's just a bunch of different bond making and bond breaking processes. When you have a series of steps, you'll have an intermediate substance formed during one step and used up in a subsequent step. It's not going to be seen as a product in the overall reaction because it'll be consumed. So it'll be, let's say, for example, it's made in step 1 and then used immediately in step 2. So when you merge steps 1 and 2 together, they would cancel out. When you add elementary steps together, you need to get your overall balance equations to match, and the mechanism that you come up with must agree with the experimentally determined rate law. So if I have a experimentally determined rate law, rate equals K times some concentrations raised to some, sorry for this handwriting, what happened to me? A stroke? If you have an experimentally determined rate law, then the mechanism's rate law that you come up with has to match your experimental rate law. So the purpose of kinetics is to learn about these elementary steps, and this is a lot of like biochemistry and physiology applications. You look at, the overall process of photosynthesis, for example. There's a ton of elementary steps involved in that. So vocabulary that you need to know. You need to know that an elementary step is a simple step that comprises, I guess, the right word, or that when I merge it with other elementary steps, it gets me an overall reaction. Also, we need to look at molecularity. So when we were looking at rate laws, I said that you cannot determine the order of a reaction by just looking at the overall process. But if you have the step-by-step process and the elementary steps, you can determine the order of each reactant from that. So by looking at, this type of equation, I can't tell what the order of the reaction is. But if I have the step-by-step process, whatever this might be, I can determine rate laws for each of these baby steps. Molecularity describes the number of molecules that participate in a collision. So unimolecular would be like what I drew here. There's only one thing, that's first order. If I have 2 molecules colliding, that's second order. So that could be this. That could be a bimolecular step, Or I could have this. That would be a bimolecular step. There's two separate things there. Termolecular is if you have three reactant molecules colliding. This is going to be very rare because the angles would be important and the odds of it happening would be pretty slim to none. So this is the step-by-step representation of this overall reaction. So nitrogen dioxide plus carbon monoxide makes nitrogen monoxide and carbon dioxide. So just looking at this overall process, you're like, oh, I just take one of these and move it over to there. But it actually happens in two different steps. The first step is taking two NO2 molecules and colliding them and bumping an oxygen over to make NO3, nitrogen trioxide, nitrogen monoxide. And then we take that nitrogen trioxide, collide it with a carbon monoxide molecule, and bump an oxygen over here. So step one, we would say that is bimolecular because there are two molecules colliding. Step two is also bimolecular because I have two molecules colliding. Something else you could see here is this NO3. NO3 was made in step one, used in step two, and does not appear at all in this overall reaction. So we would say that NO3 is an intermediate, which we'll go over more practice with that later. Now, if I take these two equations and I add them together, I should get them to add up to the reaction that's listed up here. So I can combine things and cancel. I have two NO2s here on the left. I have one NO2 here on the right. So this one would be gone, and this one of these would be gone. That leaves me with one NO2. Boom. I have the NO3s, which cancel out. And notice there's no NO3s in my overall equation. I have a CO here, CO here. I have nitrogen monoxide on a product, and I have carbon dioxide on a product. So adding those two steps together and canceling out the intermediate and anything else I'm able to cancel out gives me the overall reaction. So if I have, again, elementary steps, I can determine the rate laws for those elementary steps just based on the stoichiometry of the equations. So I cannot determine a rate law from an overall reaction, but I can't without data, but I can write a rate law for elementary steps from the stoichiometry of the reaction. So this first step, this is unimolecular, unimolecular, so that is the rate law for this simple elementary step. This would be a bimolecular step, so it would be first order in A and first order in B for a second order overall. This would be a different bimolecular step, and it would be second order in A. And this would be an example of a termolecular step, and I can write the equation like this. So again, these rate expressions can be written for elementary steps just by using basically the stoichiometry or the coefficients, but I cannot write a rate law for an overall reaction just by using coefficients and quantities. I need experimental data. More molecules I have, the more collisions I'll have, the faster the rate will be, the faster they're moving, the more likely they'll collide, yada, yada. Okay. So look, here's an example question. So nitrogen oxide is reduced by hydrogen to give water and nitrogen gas. This is my overall reaction. One possible mechanism to account, so this is step one, step two, step three. What is the molecularity of each of these three steps, and show that the sum of these elementary steps yields the net reaction. So this first step, would this be unimolecular, bimolecular, or termolecular? This would be bimolecular. How about step two? That would also be bimolecular. And step three would also be bimolecular. Now, show that the sum of the elementary steps yields the net reaction. So I want to see that all three of these steps add up to this process. So, I mean, I would prefer if all these arrows were lined up just for visual sake, but they're not. Okay, so let's start canceling things out. So we have an NO2 on the right and NO2 on the left. That would be an intermediate. We have two H2s on the left and nothing to cancel them out, but I have two H2s on the left in my overall process. I have two NOs on the left, two NOs on the left. I have this N2O canceling out here, so that's another intermediate that was made in step 2 and used in step 3, so those cancel out. And then I have nitrogen molecule and two hydrogen. So this could be verified. It does add up to the overall reaction. What I can also do here is if I have the elementary steps, I can come up with the rate law for the overall reaction from the elementary steps. When we look at a set of reactions, a lot of times you'll see the word slow or fast written next to those elementary steps. An overall process that occurs in multiple steps can only go as fast as its slowest step. So it's like if you're running a relay race, your team is only as successful as your slowest participant. They limit the progress that you're able to make. So in a multi-step reaction, the slowest step is the rate determining step. It therefore determines the rate of the reaction and the molecularity of the overall reaction. This is very important. The experimental rate law, so whatever rate law I get from a set of data, by varying concentrations, it must agree with the slowest step. So here is an example. This is the overall reaction. Here is the rate law that was determined experimentally. Okay, so notice in this rate law, it is second order with respect to NO. So we also have another reactant here, right? But it's not mentioned in the rate law. So what would be the order of the reaction with respect to the CO if it's not appearing? Right, it would be 0 order, because if I raise this to the 0 power, this would be 1, and I don't have to include it. Now, it lists these two steps in this mechanism. We have the slow step and fast step. The slow step is written first. I can write a rate law for an elementary step. So the rate law for this step would be rate equals K times the concentration of NO2 squared. Because I have two NO2s, I would raise that to the second power. Again, I can write this rate law because it's for an elementary step. The rate law that I write for this slow step must agree with the rate law I'm able to derive experimentally. And it does. So this would be an acceptable mechanism for the reaction because I am able to write that rate law. The other criteria that I need to meet that would say, okay, this mechanism makes sense, is that if I add up my two reactions, I should be able to get my overall process, and I do. So here's my NO2, here's my CO, here's my NO. Oh, that's a typo. Sorry. That should be a CO2. So I am able to add them up. So there's two criteria that need to be met. I need to make sure my slow steps rate law matches my experimental rate law, and I need to make sure that when I add the two steps of my, or however many steps of my mechanism together, I can add up to the total. So here is another example. So this is for this overall reaction, here's the experimental rate law. Okay, so again, the orders that I got from this experimental rate law do not correlate to the coefficients in the overall balance equation, and that's okay. This rate law was determined experimentally by gathering concentration and rate data. Which step in this mechanism is the slow step? So I need to pick the step whose rate law, which I can write, matches the experimentally determined rate law. So what would be the rate law for this first step? Rate equals K times the concentration of hydrogen, and that would be raised to the first power because its coefficient is 1, times the concentration of nitrogen monoxide raised to the second power because its coefficient is 2. The rate law for this step would be N2O to the first power, H2 to to the first power. So the slow step rate law would match my experimental rate law. So I know that step 1 is the slow step. Don't know what happened there. So we can also look at a mechanism and determine if there's any intermediates present, meaning they're produced in an early step and used in a subsequent step, and they don't appear in the final balanced equation. So it's basically if I have a product in an early step and a reactant in the following step, that's an intermediate. And you notice that doesn't show up anywhere in my overall reaction. Okay, so how about this one? Balanced equation for the reaction of the gases nitrogen dioxide and fluorine. So there's my balanced reaction. The experimentally determined rate law is this. So experimentally, I know that it's first order for NO2 and it's first order for fluorine. That does not match the coefficients, but that's okay. A suggested mechanism for this reaction is, here's my slow step, here's my fast step. Is this acceptable? So are these two steps an acceptable mechanism? I have to be able to add them up to get my overall, and I have to get to make sure my slow steps rate law matches my experimental rate law. So does that first bullet work out? Can I add these two reactions together to get my overall process? So I would merge those two, that's two NO2s. The fluorines would cancel out. I make a fluorine atom in the first step and I use it in the next step, so that's an intermediate. Sometimes that's a question on free response. Label the intermediate. Okay. What am I left with? Here's F2 and 2 of these. So yes, they add up. Does the mechanism agree with the experimental rate law? So this slow step, if I write the rate law for the slow step, rate equals K times NO2, and that would be raised to the first power because that's its coefficient, times concentration of fluorine, that would be raised to the first power because of its coefficient. Do those match? Yes, so that would be an acceptable mechanism. Here's another example question. Write the rate law for the mechanism. So now I'm not given the overall reaction. That's actually one of the questions I'm being asked. I can write the rate law though because the rate law is written based on the reactants in the slow step. So this would be rate equals the concentration of C4H9Br, and that would be raised to the first power because it has a coefficient of 1. So that's my rate law. What is the overall balanced reaction? So now I will go through and I cancel things out. So that gets canceled out. So that's an intermediate. Here's another intermediate. And that's it. So now I add the rest of the stuff together. So this and this for reactants. C4H9Br plus 2H2O produces, so I have this bromide ion. I have C4H9OH, and I have H3O plus. What are the we kind of already said that. The intermediates in the mechanism would be the C4H9 plus and the C4H9OH2 plus. Those are the ones in green. So that could be a typical AP free response question. Now, if you look at a mechanism and the first step is not the slow step, if it's a fast step, I'm going to show you how to come up with a rate law from that. Okay, so here's our mechanism. All right, so for this one, the first step is fast and the second step is slow. We can only write a rate law based off of a slow step being first. Now, here's the thing. When you see these reaction mechanisms, if the fast step is written first, normally it's going to be written as an equilibrium problem, or an equilibrium equation. If it isn't, just pretend that it is. It's going to work out fine. Okay, I think this jumped around a little bit, but here's what you're going to do. Sorry if this is out of order. I can't have this, if this is the slow step, right, which I would write my rate law from. Rate equals K times NOBR2 to the first power times NO. That can't be my rate law because my overall reaction doesn't have the NOBR2 in it. So this is my overall is 2NO plus BR2 produces 2NOBR. Okay? My rate law can't have stuff in it that's not present in my overall reaction. So what you need to do here is substitute the other side of the fast step, because if this is equal to this, I could just use them in substitution for one another. So if I take this side and substitute it in for that NOBR2, so I have NO plus BR2 plus NO as my slow step now. Now I can write a rate law for this. Rate equals NO, and since there's two of them, square, times BR2. Here's my overall reaction. NOs and BRs are present in there, so this would work. So the rate of the overall reaction depends on the slow step. So this is the slow steps rate law, but so that's the second and elementary steps rate law, but I can't use that as my overall rate law because this is an intermediate. It was made during step 1 and is used during step 2, and I can't have an intermediate in my rate law. So we got to figure out something to do with that. We got to substitute something in for that. So what we do is we use the fast step and the fact that it is an equilibrium to substitute the other side of it into the slow step and solve from there. Let me show you. Wait, hold on. Let me show you this example from start to finish since it's all in one slide. So here's my overall reaction. Here's my step 1. Here's my step 2. Write the rate law. I cannot write the rate law for this overall process using a fast step first because the fast step does not give me my rate. My slow step does. But the fast step is equilibrium. So D is equal to A plus B. Cool. So I can take this A plus B and substitute it into my slow step in position D. So now my slow step reads like this. The A plus B part plus the B part that was originally there produces C. I can write a rate law for this. Rate equals K times concentration of A, that would be to the first power, times the concentration of B, and that would be squared because there's two of them. It's probably easier to see all on one page. So basically, if your fast step is written first, you substitute the reactants from the fast step for its equivalent in the slow step and write your rate law from there. Here's another reaction that kind of summarizes all these reaction mechanisms problems. So here's my overall reaction. It's proposed to occur using the following mechanism. So I have step 1 is fast, step 2 is slow, step 3 is fast. Prove that the mechanism is consistent with the overall reaction. What are the intermediates and what is the rate law? Okay, so proving that the mechanism is consistent with the overall reaction, that would mean just add these 3 steps together and make sure we get the overall process. So the z's would cancel out, the x's would cancel out. Okay, so what am I left with? 2a, check, plus 2b, check, produces c, check, plus d, check. So adding everything up is cool. What species in the reaction are intermediates? Well, the z and the x's are intermediates because they're made in an earlier step and used in a later, oops, should underline the x there. Used in the later step. Now, what is the rate law for the reaction? The rate law is based on the slow step. If the slow step were written first, we would write it and be done with it. But since the fast step is written first, we need to substitute the reactants from the fast step into the equivalent portion of the slow step. So z was the equivalent of a plus b. So we would put the a plus b in this spot. So rewriting this, it would be a plus b produces c plus x as my slow step. Now I can write my rate law. Rate equals k times the concentration of A to the first power times the concentration of B to the second power. And if there were experimental rate law, it should match up with this. We're going to do some more practice with reaction mechanisms in class. Thanks for coming.